The pretty crystal is brushite. It's a high-resolution transmission electron microscope picture hand-colored by the artist. And the subject here is brushite, a very simple crystal, calcium phosphate. And the implication, the title, is to lower the brushite supersaturation below 1. I'm saying this to doctors. I'm saying this to patients. And as I say at the beginning of the text, the title is my story's conclusion. The gist of it is this. The crystals in plaque and in plugs are hydroxyapatite. But you don't really make hydroxyapatite de novo. You tend to make it from brushite. Of course, most stones are calcium oxalate, and the phosphate they have in them is hydroxyapatite. You don't generally make calcium oxalate de novo. You make it on plaque, you make it on plugs, and when it forms in solutions like urine, it seems as though it forms from brushite. So brushite's like a starting point, and keeping that starting point from starting, that's what you do when you get the supersaturation for brushite below 1, just seems like a really prudent, nifty, great idea. Now, you might say, all right, it's a great idea. How about a little bit of science? What I've done is brought one big paper. But before I come to the big paper, I want to go back to Charlie Pock's work back in the late 50s, early 60s. Charlie added calcium to human urine to get crystals. And 25 of the 28 samples he did that in formed brushite as the first crystal. Later on, you get hydroxyapatite, or you could get calcium oxalate. This business of it being the first crystal was very important, and it led him to do a lot of work on brushite. And I think in that sense, Charlie was a forerunner. Now the present work, which is a wonderful piece of work, it looks like this, if you saw the reference. It's by Professor Tang, Nankolis, and colleagues. And I'm going to parse through it in this article and tell you a little bit about what they did. Not going to read you all these technical details. I'm going to show you the figures. The first figure shows an experiment. There's a reaction vessel, and the reaction vessel is fed by 2 pairs of pumps. One pair of pumps can pump in calcium and phosphate together. It's triggered off by sensors that sense when a crystal is taking up calcium. Calcium will go down in the vessel. And when the vessel solution pH is falling, it's becoming more acid. And that occurs when you make brushite crystal. The reason for it's in the article, you can read it, but to take my word on it, is you make brushite, the solution becomes more acid. And along this axis here is the volume of titrant that's being pumped in to replace calcium and phosphate as brushite would grow. And why would brushite grow? They added brushite seed crystals right here at this point. So they have a solution. You say, well, what kind of a solution? Well, the solution is supersaturated. And the supersaturation is 1.2-fold for brushite and 1.8-fold for calcium oxalate. And it's just waiting there, doing nothing for about nearly 100 minutes. They put the seed crystals in right here. And you can see the calcium and phosphate pumps go on. It's called brushite pumps. And then they stop. They stop pumping. A second pair of pumps, which we call the calcium oxalate monohydrate pumps, they pump calcium and oxalate. Well, how do they know to pump calcium and oxalate instead of the other pair pumping calcium and phosphate? But when you make calcium oxalate crystals, the pH of the solution does not change. So, as you make the brushite seeds grow, these pumps are turning on as well. What this is saying is more calcium is disappearing from the solution than can be accounted for by the pH. And so this system begins pumping. Calcium oxalate crystals don't change the pH. Here, there's no more phosphate being pumped. The calcium pump for the phosphate side is shut off. And the pair of pumps for calcium oxalate are pumping and pumping and pumping, and this thing is going straight up, and they end the experiment. Now, what is SG1 and 2? Well, they sampled the solution. At the beginning, the samples at SG1 was 40 milligram. That's what they got. And it had a molar ratio of calcium to phosphate of 1, and that's what you would get with brushite. That's what you expect. SG2, which is after the brushite's no longer running, there's less crystal, and it has a ratio of phosphate to calcium of 0.72. In other words, it's not as much phosphate for the calcium. SG3, brushite's been stable a long time, and the calcium oxalate monohydrate pump has been going on a long time, and this has no phosphate, none at all. So what are we looking at? Well, it isn't just that you made the brushite and stopped making it. It's that you made the brushite and the crystals turn from brushite to something like a mixture of calcium oxalate and brushite. That's that ratio of 0.72. And at the end, it's nothing but calcium oxalate. All the solids are now a ratio of 0 phosphate. So you didn't just make calcium oxalate, you unmade the brushite. Wow. So who says you unmade it? Well, this is what things look like. This is a transmission electron microscope image of the solution. This is the brushite crystals, and the panel A is the SG2. That's where things were kind of part way along. The brushite was not growing anymore. And what you can see is the surface of these round crystals is brushy looking, it's fuzzy looking. And where the arrows point, there's tiny kind of rectangular crystals growing. That's calcium oxalate monohydrate. So they're actually growing right on the surface here. And the surface is all roughed up because it's coming apart. What's this? Well, this is a tricky, complicated thing. This is an atomic force microscopy. A very, 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 very tiny stylus sweeps over the surface of this crystal like an old phonograph needle. And it's so tiny, it can pick up the stacking of the calcium and the phosphate atoms as they make up the surface growth of the crystal. That's these zigzags. It grows that way. And that's what it's supposed to look like. In panel C, there's holes appearing in these plates. They're being broken up. Here in panel D, you can actually see a growth plate with a hole in it. There's a pit. Here's another one. Here's another one. They're being dissolved. In panel E, there's no more growth anything. It's just calcium oxalate sitting there. So the seeds go in, the calcium oxalate begins to grow and takes up the brushite and disappears it, gets eaten up. Oh. Well, how does that happen? The oxalate is so powerful an attractor for the calcium, it pulls it right off the surface of the brushite, makes calcium oxalate, keeps doing it. Why did the seeds stop growing? The calcium leaving the surface is equal to the calcium coming on. Obviously, phosphate is leaving at the same time. The second experiment, which is basically the same figure showing it twice, they let the solution, 1.2 supersaturation for brushite, 1.8 for calcium oxalate, they just let it go. 1,400 minutes is a day. Nothing happened. The sensors are running, the pumps are waiting. At around a day, it starts making brushite. How do you know? Well, the brushite pumps are running. The pH is falling with the calcium. Soon after, here comes the calcium oxalate. And then they've got these solids, N1, N2, N3. The solid at N1 is brushite. Ratio of phosphate to calcium, 1. By N2, it's brushite with calcium oxalate monohydrate on X-ray diffraction. That's how physicists determine what's in a crystal. Ratio is 0.67. By N3, there's just the tiniest bit of calcium oxalate, of brushite. Ratio is 0.16. By 4, there's only calcium oxalate. The brushite's been extinguished. Here's some gorgeous pictures. This is the SEMs of N2. N2 is right here. Certain areas, pure calcium oxalate, no phosphate, all calcium. In this hole, which is in the core of this bunch of crystals, brushite. So it doesn't just show you that you're converting calcium oxalate to brushite. It shows you that the core is still brushite. It's all happening on the surface. It's pretty much, I call it the perfect finish. The oxalate attacks the brushite from the outside, rips the calcium off the surface, and replaces the brushite. What does this mean? It means what it says. You make brushite first, just like Charlie said. The oxalate takes it apart and makes it into calcium oxalate. So what is this about the hydroxyapatite? Why haven't I showed you how that gets made? Other papers. Here's an example of that kind of paper. Here's a whole article which I wrote about just that problem. You can go read it if you'd like. It's a whole big deal. Here's a physics paper, kind of pretty looking. And I could review this for you, but I don't want to. It's going to double or triple the length of the article, and it's very technical. Maybe another time. What about plaque and plugs? They're hydroxyapatite. Calcium oxalate forms under it. Same story? No. Calcium and oxalate can't replace hydroxyapatite. It's too strong a crystal. What happens is the calcium oxalate grows right over it. And if you go back to this article on the site, you can read it. What about plugging of tubules? The urine washes over the ends of the plugs, calcium oxalate stones form. Same story. It forms over the apatite. Not the same as what I'm describing. So what am I describing? How crystals could form in the urine. Not on plaque, not on plugs, but in the urine. Does this happen? Sure. How often? I don't know. This last set of experiments is just luscious. Here, the investigators have added a very tiny concentration of uric acid to the reaction vessel. The urine contains 0.5 to 4 millimole. They added a tenth of that. What happened? What did they do? They had the system running. What's the system? The same solution. Supersaturated 1.2 for brushite, 1.8 for calcium oxalate. They let it sit. Instead of 1,400 minutes, brushite's nucleating at about 900. That's a lot faster. Instead of 200 minutes to get to the calcium oxalate, it's more like 30 or 40. So it accelerates the whole Brushite calcium oxalate story. What about citrate? Well, we know citrate is a big deal inhibitor. We know it's a proven kidney stone prevention. It delays the Brushite onset from 1400 to 2800 minutes. That's doubling. And it delays the beginning of the calcium oxalate by twofold. So it inhibits. What about the crystals? Well, this is a calcium oxalate crystals that form on Brushite. They're kind of small. Here they are when they grow with uric acid in the solution. They're bunchy and clumpy. They could stay in the tubules. They could stay in the collecting system maybe and grow. And these are the crystals grown with citrate. They're very small. They do aggregate a bit, but they're tiny things. Well, we already know citrate's a terrific inhibitor. Uric acid's a sort of a story. I proposed when I was in my 30s that uric acid, when it's high, might promote calcium oxalate. Bruce Ettinger published a beautiful trial showing that when you lower uric acid with allopurinol, you reduce calcium oxalate stones. The mechanism has never been clear. I think this particular experiment really adds a lot to maybe why uric acid is a promoter of calcium oxalate stones. Why, when it's really high, you should try to get it down, either by a diet or maybe allopurinol. One of these days, I'm going to write an article kind of bringing allopurinol back. The last part of the article is very simple. You'll see there are Brushite stone formers, and they're the strangest stone formers on earth. Why would you make these stones? Brushite shouldn't exist, but there it is. I don't know what stabilizes it. I haven't any idea how these stones form. Finally, you could say to me, Fred, theory and science is beautiful. Do you have any evidence in the world, like real evidence, that supersaturation with respect to Brushite is a hair trigger for calcium stones, like tinder to a fire? The answer is, I sure do. All of you who read this site have seen this epidemiology. 2 female cohorts in red, a male cohort in blue, relative risk of becoming a stone former versus urine calcium, urine oxalate, urine volume goes down with volume, urine citrate goes down with citrate. Supersaturation calcium oxalate goes up, but it goes up when calcium oxalate supersaturation is above 3. Well, you say that's a 1 there. No. The funny way this was done, the supersaturation is divided by the mean supersaturation of normal people. Don't ask me why. That's 3. So this is really 3 to 6. What about supersaturation calcium phosphate? That's Brushite. Risk begins at 1. Less than 1 was the reference point. Above 1, it's already there. It doesn't progress too much either, even up to 2.9. It acts just like a trigger. What's the message? Get it below 1. Same things you're going to do anyway. Citrate, thiazide, low sodium, water, all the stuff we do. Just watch the Brushite supersaturation. Get it below 1. Harm, 0. Possible benefit, very real. George Nankelis was the brains behind the constant composition system, whose workings you just saw. He was a man I knew well. He was someone I would call a friend. He was a brilliant, sophisticated scientist, and he did a lot for the field of basic science in kidney stone disease. He died January 11th, 2016. He left 420 publications as his legacy. As for the beautiful poem by Emily Dickinson that I left behind as his commemorative, you can read it for yourself. It's a very beautiful thing and seemingly more applicable than one would have thought.